Good afternoon, this is Charlie Beine, Thermal Support, and we're about to do another one of our videos for thermal analysis. In this case, it's going to be the PerkinElmer DSC7 and configured with a dry box, an intercooler tube, and we've already got the computer set up with the TAC. And this video is going to be on the setup, startup, and operating videos. Now we're going to make the assumption that you've already got Pyrus on your computer and the system is basically set up. We will show a cabling diagram on it. But we're going to take it from that point on. After looking at, I think, our last videos of the DMA7, it was very interactive. A lot of stuff with the DMA is you really interact with the instrument. DSC7 is a pretty basic instrument, but a lot of the interaction is with the software and how you perform your method and things like that. So we're going to try to take that as a good starting point, and so you're not going to have to look at me very much. And what we're going to do is we're going to have you, excuse me, we're going to put a lot of slides in this video from some of our training courses. All right. So that being said, let's go ahead and get started. As I said before, this video is on setup, startup, and operating variables for DSC7. This also translates into other power compensated DSCs. If you're going to get a DSC7 or any of the other systems, basically what you need to have a sturdy bench, about 2 feet of space for each component, and then good, clean, dedicated power. I think it's specified 120 volts AC, 60 hertz, 20 amp. And most people say, well, can't my regular power handle that? Well, yeah, probably so. But what a lot of people folks don't realize is that PerkinElmer and most of these manufacturers, they've been doing this a long time. They make really solid electronics. These are very sensitive instruments. And the vast majority of electronic failures any of these folks ever see are due to incoming power. It's a pretty significant investment whether you're on the aftermarket side or the new product side. So power is a big deal. And so we want to encourage you to provide good, clean power that you feel confident with. Then we're going to look at a basic DSC7 setup. The subambient DSC7 setup, we're going to follow that with just the cable configuration pictures. Then we're going to confirm, look at gas pressures, confirming them, and filters. In this case, with the dry box one, having a good high quality dry filter is important. And then we're going to assume, as I said earlier, that you have that you're already set up with your computer, which is going to be a Windows XP Service Pack 2, or people are even asking for the Pyrus 10 configuration, which works on this. I don't know that the later ones do. We're assuming if it comes up and it works, that it works as well as any of the other software that PerkinElmer has allowed instruments to come up with. And then we're also going to tell you that once you get into your Pyrus software, before we even get into this video, if you look at the help file on this top of the top file menu bar, go into help, quick help is under there, and that's a tutorial for this product and for all thermal analysis. And so that's your homework. If you're a new user, quick help's your homework. So let's look at the basic DSC7. Again, 2 feet of space, good clean power. You want to confirm your gas pressures. The gas you're looking on with this one right now is going to be your purge gas, which you're going to need from 20 to 50 psi pressure. And your Pyrus help files, any of your other questions easily can be answered. Now there are basically two versions of that system. One version is that underneath the deck you have a dewar, and that dewar you can put ice water in, or you can put water in, to help control the block temperature. And then the other one has, other configuration is open underneath the deck. And with that configuration, there's a turbulent chamber on it. That turbulent chamber basically allows you to recirculate water through there, or you can come off your hose, off your wall. You can come out of a recirculator or some other type of coolant to control block temperature with it. Now the next system we're going to look at is the DSC7 ambient system, which is what you were looking at right here. Same stuff, basic requirements, all the same. Which, by the way, we're gonna as we go through here, some of these we'll go through a little faster, so that we know you can stop this video whenever you want to. So if I kind of skip through some stuff, feel free to stop and look at the slide, and hopefully there's enough information for you. The configuration options for this are typically a doer for LN2 supply, intercooler 1, which will take you down and control at minus 35 degrees C, and intercooler 2, which will take you down to minus 65 degrees C. Now let's go past that, and here we got a picture of your cable configurations. They're self-explanatory. And then we're going to go to the next page, and we have our preferred gas setup. Now, you know, we've been in thermal analysis a long time. We've seen a lot of issues. Right here, you've got one of the biggest problems that we've found is gas supplies to instruments. I think people take them for granted. It's especially in thermal analysis. You may have a gas supply. They're not always turned on. They can be responsible for detectors going bad. In this case, with the dry box on here, it's important to have a high flow rate of very dry gas. These aren't unique to us. Nordham's been making these for a long time. I think Perkin-Elmer's been selling for a long time. I'm sure a lot of other people have also. What I've got pictured is that these manifold regulators can be strung up to 6 of them together. They work great. They are configured with 1/4-inch male MPT fittings on them, so you have it's pretty common what you want to put in there. This one is shown fully together. The dry box instrument that you just saw on the slide, that basically requires 2 if you're not switching gases, and those 2 would be your purge gas, it would be your dry gas. Now, the purge gas for a DSC7 and the Perkin-Elmer DSCs, they have what they call H restrictors inside the instrument. An H restrictor is kind of a poor man's mass flow controller. And what that means is that it's a restrictor that's calibrated for basically you put 20, 25 psi in, you get 20, 25 mils a minute out. But then as long as you leave the regulator at that point, it stays at that point. Your gas is very stable. And when you're on a manifold regulator, you can look at that right behind the instrument all the time. You know whether or not your gases are on, whether they're not on, or they're on the right pressure. And then with the dry box, so with the DSC, let's say this instrument right here, we only use 2 of these regulators. One's got an 1/8-inch fitting that goes into their internal H restrictors for both sides of the sample holder. But then the other one is configured with an A restrictor. Now down here at the bottom you'll see that it has 10x the flow. So by using the A restrictor we can crank up the pressure not too high, we get a very high volume of flow, and then coming into this system we've put in a high volume gas control gas trier. And we chose one that has a indicating cartridge, so that's easily changed, and you can get very high volume of very dry gas. Now, why is that important? Well, your dry box has got a very cold detector in there. If you have the intercooler 1, it's controlling, it's trying to go to minus 60, but it actually controls at minus 35. Intercooler 2 is going to try to go to minus 100, but controls down to 65. And then liquid nitrogen. So any moisture that gets to that detector is going to show up as frost, or if it's a lot of moisture to ice. So typically we look for less than 4% humidity. The high volume gas controller really gets you down there. If you flip over to the next slide, then you can see a picture of an intercooler one. This particular analyzer, it's been on 4 hours. All that frost came in there basically when it was initialized, and frankly because we don't like to wear gloves around here and it sucked the moisture off our hands. But we did it. So that level of frost, a little bit more, is what you typically can expect. We've seen these, I can't tell you how many times they're just loaded with ice. Well, that's not so much a good thing. And so the reason they get like that is there's too much humidity in the purge. They don't have enough flow in there. In really bad places, you might want to put some desiccant in there. And there's a number of reasons, but you don't have to put up with that. And by having good solid gas, tri-gas controllers, you can really avoid it pretty good. And by the way, when you're running cold like this, turn it off at night, or at least turn it off and let it warm up once every 24 hours and set the instrument on 100 degrees C. So you can get rid of every bit of that and start over. Every once in a while somebody will have this on and they'll run it for a month and they'll never turn it off. And they gradually accumulate ice. I'm going to flip right back to that just before that. And I want you to, as you look at this, we've got a little note over here. You can contact us for purchase, or you can look in our library. Folks, we don't make any money on this. You know, this is one of those things that's essential for for you to have good quality instrumentation and control. And we purchase those from Nordrum. We'll tell you exactly where to buy them. We purchase the restrictors from PerkinElmer. We'll tell you where that is, and we have information there that tells you how much you need for each one. The same with the gas control. So if you want to put it together yourself, we would love to help you. Go there, we'll give you whatever information you need. If you'd like for us to do it, we're happy to do it. We're going to end up charging a couple $100 for all of our time, but we're not going to break the bank on that. So let's go back and let's continue with our setup, startup, and operating variables. Now, when we start up this analyzer, so we've got this analyzer set up. We've got all the system connected. We've got good gas control on it. What we want to do is we want to turn this thing on to the computer. Well, the first thing you have with this particular analyzer is a startup sequence. You have your computer first. By the way, you can do the analyzer first if you want to. The key is the TAC, but officially it's CAT, C-A-T, Computer Analyzer TAC Controller, and then go with your Power software and link them up. Now, once you've done that, you want to make sure that all your components have been on, specifically whatever you're using for a cooling device. If you're using, if the instrument's running at room temperature and you've got water in there and it's all stable, you can just start right on in. But if you've got an intercooler that's going to try to take the block to -60, and intercooler 2 is going to try to take it to -100, our liquid nitrogen is going to go way down there, then it's going to take a little bit of time for the instrument to equilibrate, for the block to stabilize. So when you so you need to live a little time. And by the way, stabilization, you can tell when you're stabilized if you're in if your temperature is controlled. If you'll notice when we started this video, the ready and the control light were both on. The DSC7 is not a heat flux instrument that has thermocouples. This is a power compensated DSC with two very small 1 gram furnaces, and it has and the way you know that you're at a particular temperature is when the control light is on. It is extremely accurate. It is extremely fast. It can heat and cool at 500 degrees a minute, and so it has enormous capabilities. It's still, but you look at the control light instead of getting an actual thermocouple representation. Now, First thing we're going to do, we're going to have it on, we let it sit, and we're going to let it sit for 45 minutes or an hour. And we're going to go ahead and set up a baseline. We're going to set up an Indian. So let's go over the next one. Okay. Well, what I did here is I went ahead and included a stabilization run. You've turned it on. If you were to immediately start it up, this run was done with indium and an intercooler tube. This instrument had been on for half an hour before I did the run. If you look at the onset temperatures, they're very close on the left-hand side, but it had only been on for close to half an hour. It was not completely stabilized. And so you'll notice the first 3 runs, it takes the 3rd run before the baseline becomes stable. And then over the next 3 runs, it truly is stabilized and you're in specification for the instrument and you're ready to go. And it's going to stay there. It's not like you have to worry about this all day. You just need to give the instrument time to warm up once you're stabilized, once you're operating. Okay, so yeah, let's go ahead and continue on with our initial setup. And what we're going to do is we are looking for general instrument verification. This isn't for calibration, it's not a performance verification. You want to find out if this thing works like it's supposed to. We all do. So, first thing we're going to do is we're going to set up an initial baseline. And we're going to do that with scanning 80 degrees a minute. If you've got one of our instruments, you're going to have a service data and a service method already in there that's going to have 80 degree a minute baselines, full range, or over your range of operation. You'll have repeat indium runs in there. Otherwise, you'll have to go in there and just set them yourself. It's not a problem. Feel free to call if you do have any trouble. But we're going to run a baseline. And we're going to be looking at minimum ranges. For instance, if you've got an intercooler, if you've got an intercooler 2, we're going to run a baseline from -50. If you got liquid nitrogen, we're going to run from -150. So, for you set it up. Everybody's going to be a little bit different. What you really want to do is make sure that you've got good baseline control. So let's go to the next slide. I want to show you something. This is a baseline. This is not the baseline that hopefully you're looking at on your instrument. I put this here to tell you a couple basic things. Number one, the adjustment limits for a DSC7 for slope and balance max out at about +88 and -88. What you're looking at is a DSC that has been very contaminated, that has a lot of curvature from 50 to 450 degrees. And when you see this, all the deviation from the straight portion of the curve is all curvature. That is what you'll work with the balance. Every bit of the straight portion going on out is all slope. Okay, so hopefully you don't ever see one of those. It's interesting that it's our belief that an enormous percentage of the sample holders ever replaced that have gone bad really could have been avoided by the right sample pans, by a huge issue is not having purge gas when you have dirty samples, things like that. So if you've been having sample holders go bad, feel free to give us a call. We're happy to help you out. Let's go over and look at what a baseline really ought to be looking at. Now this one has already been adjusted. In this case, it happens to be the instrument that you saw that was using for this video. And this baseline went from 50 to 500. And what we do is we look at 2 things on this. We look at the noise level and we look at the peak height. Now the peak height, looking at the curvature, will tell us how much we adjust our balance. Basically, this one is 0.6 milliwatt peak height, which would mean that that 0.6, if we wanted to adjust the balance, we'd make it a -0.6. If it was a minus 0.6, we'd turn the balance to plus 0.6. To put this in perspective, the minus 0.6 is pretty much within the range of a brand new, very expensive sample holder. This happens to be a rebuilt one. And then the noise level for this one is almost non-existent. It's way down there, the numbers are down there. This is not representative of every sample holder, whether it be new or refurbished. All of them are different. They're like being two independent furnaces. It's like a Ferrari. I mean, this thing is, they all have their own characteristics, but you should be able to very quickly come up with a decent baseline. And it's a great starting point. If you were to calibrate full range of this baseline, you'd be within spec. On the Perkin-Elmer specs for this instrument is 0.1 degree centigrade for accuracy and precision for the temperature. Now let's flip over this to the next one, and there we go again. That's that unstable block temperature. Now, why am I showing you this? The reason you've seen this, and you're going to see it again, is simply that there is that because of the fact that you're watching this video, you're probably the main user for your equipment, and are a new user to your equipment. But historically, for almost any industry, users usually get one training course, and then they train the next guy, and they train the next guy, and they train the next guy. Or maybe at some point in time they add on another accessory and never get trained on. And one of the things that often slips by is that folks will come in on an instrument after they've had for 10 years, and you've got a user that's been there 6 months, and they turn everything on and then they start running. Well, that's may have been common knowledge in the company 10 years ago when it started. Unfortunately, along the way, for a number of really good reasons, it got lost. So we like to show that slide over and over again. Now let's go to the next one. Here's a repeat NDM with a stable block temperature, and this is the way they ought to look. We just put this sample in. There are 3 runs here. If you'll notice that it goes from the top, 1, 2, 3, going down to the bottom. This thing has got enough data points to give us a good representation of what's going on. The first onset is 157.66, and the next 2 are 0.67 and 0.67. I know the spec is 0.1, but if you're not moving a sample in there, this instrument is capable of enormous precision. And the first run, sometimes you'll see it off more than that. And the reason is that's an initial melt. You put a sample in there, you put the pan in there, it does the initial melt, and then it's stable. The sample itself is stable, and you're seeing better numbers on the second and third. Now, this is a big deal for us because this is dead on. It repeats over and over. This is not a calibration. This is precision. It's a performance test. Is this really working right? Calibrating is simple. You know, software takes numbers and they turn them into a different number. What you want is an instrument that's rock stable. It's going to give you predictable results time after time, and then take those results and let the software manipulate it so that you're getting the right numbers. Another thing here is if you look at the delta H, well, Perkin-Elmer's spec for that is 0.1% for precision and 1% for accuracy. Well, this is well within the 0.1% on that. You've got 29.643 and 29.648 joules per gram. And again, this is uncalibrated. We would open up, we'd go into calibration, we'd make those numbers to turn into 156.6 and 28.45, I think. All right, so we're in good shape. The instrument's working right. Let's move on. So now that we're in it, and we say, all right, the instrument's working right, let's just talk a little bit about operating variables that you can look at with the DSC. We've got balance considerations, got block temperature stability. Yeah, I think one more time on that one. We have heating rate effects, sample size, and sample pans. So first of all, balance considerations. There are people who sell pre-weighed samples, pre-weighed reference materials, and that's fine and good as long as you don't weigh your samples. If you don't look for any heat data on your samples other than the actual melting temperature or the onset temperature. But the reality is our opinion that you should never buy, that two things you should never do. You should never buy a pre-weighed sample, and number two, you should never weigh your samples on two different balances. Whatever balance you weigh your reference material on has got to be the same balance you weigh your samples on. That way, if somebody forgets or somebody puts a bad calibration into your balance, you know, your samples, your reference material and the sample materials can be weighed on the same balance, and so the errors are going to cancel each other out, and you're not going to look back 6 months from now and find out that you had a problem and realize you put out wrong data for a long time. So we are the next one again, block temperature stabilization. You've seen that enough. I'm sure you're getting frustrated with me bringing that over and over again. Let's move on to heating rate effects. Now, one thing that's common to all DSC is that data is taken over time. So if you got slow, if you're running your sample slow, you're going to get a small peak. You run it fast, you're going to get a big peak. And that's really useful when you heat to pull out very subtle transitions in your samples you might not see otherwise. It's also with this being a power compensated DSC, it also makes this instrument capable, this instrument is capable of actually doing hyper DSC applications. Now, what is hyper DSC? It's basically running, say, 10 times what a normal DSC run would be, and then you can really pull out information from your material. You can put off other information from happening in your material. There's a lot of stuff you can do, but you need to remember, if you decide to do very fast analysis with this, it may require lower starting temperature, because it's going to take a few seconds to stabilize once you start doing a run. And by the way, if you're starting to do a run at 5 degrees a minute and you're starting to do a run at 300 degrees a minute, it's going to take a little bit longer to stabilize. And also, the total mass of the sample pans can have a lot greater effect. So if you typically, when you do hyper DSC runs, you use very, very low mass sample pans. I think people even put it in punch out of aluminum foil. But anyway, that's just a little bit about heating rates and the fact that the instrument can do much faster, and there's a lot more information than that in our application notes on the website or in our training courses. Next thing, sample size makes a big difference. There are folks out there who have an undefined onset for their samples, and they typically will use a peak height for doing their temperature calibration. Well, that's problematic if you don't have the same mass, and this is a very small representation of what happens. Basically, when we're running indium here, and in one case it's about 7 milligrams, the next case it's 13 milligrams, so it's not quite half. And you can see we've got a pretty nice shift in the actual peak height of the sample. So this could be a lot more dramatic with different weights, different materials that don't come off so much. So if you're going to be using peak position for calibration, remember that it is mass dependent. And what else we got? The next nice thing to remember is sample pan effects. When you run your samples, always calibrate with your reference materials in the same sample pan you're running your samples with. Now, yeah, I know different materials can be more challenging in various pans. There's ways to get around that actually work very well. But just to show you how different pans react, you can see that the standard aluminum pan is a 0.1 millimeter thick aluminum. A 0.2 millimeter thick aluminum pan is going to be shifted over there to the right. And then you can see the stainless steel and then the ceramic pan. Let's see here. And yeah, that's pretty much it for the sample pan effects. Matter of fact, that's the end of the setup, startup, and operating video for this series instrument. Look for the next video. We're going to do DSC7 maintenance, calibration, and performance verification. Yeah, I hope that helps. You should see on there that how to contact us at thermalsupport.com. We'd love to hear your feedback. Take care and have a great day. Thank you.